Section 10.7, Taylor Polynomials. Think back to Calculus 1 and the concept of the linear approximation of a function at x equals a. This is just the equation of the tangent line to f at x equals a, and hopefully a picture comes to mind. So we visualize the function y equals f of x. We pick a particular x value, we'll call it a. The associated y values for the function is f of a, so this would be a point that we know. And then the idea in Calculus 1 was to find the equation of the tangent line to y equals f of x at x equals a. In other words, the graph of this red line. And so we calculated, you can calculate the equation of that tangent line, also called the linear approximation of f at x equals a. And the formula for that was L of x, L for linear approximation. L of x is f prime of a times x minus a plus f of a. And so the graph here shows that the tangent line here is tangent to the function y equals f of x at x equals a. In other words, it passes through the same point as f at a. It passes through the point a comma f of a, and it also has the same slope of f at x equals a. And the idea with a linear approximation was that if you think of f of x as being a complicated function and you think of a linear function as being a really simple function, because it is, then this complicated function f of x can be approximated by this much simpler function L of x for x values that are near a. Now exactly at a, these two functions agree, so really we think of if we were to scoot off of x equals a little bit and plug those x values into the L function, they would give us very close to what we would get when we plug those x values into the f function. So the key question that we have here is, okay, in Calculus 1 we did this with a first degree polynomial, in other words a linear function. We found this approximation to f using this first degree polynomial. And so the question before us now is, can we do this same thing for higher degree polynomials? So one other thing that we should point out is not only is this a linear approximation, it's actually the best linear approximation that you can find for f, in the sense that it matches f in both function value and first derivative value at a, and it's the only linear function to do that. So that's why we call it the best linear approximation. So for example, can we find a quadratic approximation? And we'll be even more ambitious. Can we find the best quadratic approximation to f at x equals a? You could think of it as a sort of tangent parabola. Now that isn't exactly what's happening. We'll talk about what we mean by that. But what if we wanted to find the best quadratic approximation to this function f at this point? Or what if we upped the ante even more and said, can we find the best cubic approximation or third degree polynomial approximation to our function at x equals a? And we could keep doing that forever. So why don't we just play this game to try to understand it better? Let's find the best quadratic that's centered at x equals a. In other words, we want this to be an approximation about x equals a. So instead of writing our parabola, say, in the standard form, we will write it as some constant times x minus a, quantity squared, plus some other constant times x minus a plus a third constant. So we're treating a here as a value that we know, just like in this picture. We're thinking of this as a fixed x value that we know. And so the unknowns here are c2, c1, and c0. So those are the values, the constants that we want to be able to find. We need to find the coefficients, c1, c2, and c0, such that q of a equals f of a, q prime of a is f prime of a, and q double prime of a is f double prime of a. In other words, this quadratic is going to match f in function value, first derivative, and second derivative. Notice, because it's a second degree polynomial now, we're upping the amount of derivatives that our new function has to match with our old function. So our new approximation has to match with our original function. Now, if you just evaluate this function at x equals a, this zeroes out and this zeroes out, and so you get q of a is the number c naught, and you want those to match, so q of a being c naught is the same as saying, or q of a being f of a is the same as saying c naught is equal to f of a. So c0 has to be f of a, so 1 down, 2 to go. If you take the derivative of this with respect to x and then evaluate this at a, well, first let's take the derivative. Q prime of x is this. We evaluate this at a, x equals a. We get, when you evaluate this at x equals a, this zeroes out, you just get c1. And if we want q prime at a to equal f prime at a, that forces c1 to be f prime at a. So now we found the value of our second constant. It's f prime at a. And the last constant, if we want the second derivative of q at a to equal the second derivative of f at a, well, let's go calculate the second derivative of q with respect to x. Let's evaluate it at a. Notice there's no x's here, so when you evaluate it at a, you just get the constant 2c2. But we wanted q double prime at a to equal f double prime at a, so that means this equation must be true. We can solve this for c2, and we get that the constant c2 must be f double prime at a over 2. So when we take these three numbers and we plug them back in for these three constants, we see pretty quickly that our quadratic approximation is f double prime at a over 2 times x minus a quantity squared plus f prime at a times x minus a plus f of a. Notice if you stare at this quadratic approximation, it is indeed a second degree polynomial approximation. We can tell that this is a second degree polynomial. But more than that, notice this is our first degree polynomial approximation. This is L of x if you scroll up and look. This is L of x. So what we effectively did is we added on one more term, and it's a higher power, a second power term, to our old approximation. So you can see that this new approximation built on our old approximation. And that's an idea that we'll see that keeps coming up throughout this section. So humor me, and what if we played the game again and we wanted to find the best cubic approximation at x equals a? So in other words, we want a third degree polynomial that's centered at x equals a. And I've already used the letter c, so I won't use c for cubic, but how about we'll call it p3 for third degree polynomial. So if we do a third degree polynomial, it should look like some constant c3 times x minus a to the third, plus some constant c2 times x minus a squared, plus some constant c1 times x minus a to the first, plus some constant c0. Now, if you just go and do exactly what we did before, we said, hey, if it's a third degree polynomial, then when it was a first degree polynomial, it needed to match, the approximation needed to match the function in function value and first derivative. When it was a second degree polynomial approximation, it needed to match the original function in function value, first derivative, and second derivative. And so now that it's a third degree polynomial approximation, it still needs to match the function and function value at a. It needs to match the derivative at a. It needs to match the second derivative at a. But now we're going to ask even more, it needs to match the third derivative at a. And if you notice when we play this game, we've imposed 4 conditions, and those 4 conditions are going to help us, allow us to find those 4 constants. We have 4 constants, so we need 4 conditions. Now, I'm not showing all the details here, but if you play exactly the game that we played in our last 2 examples, the way that it comes out is that C0, the constant, is f of a, C1 is f prime at a, C2 is f double prime at a over 2, and lastly, C3 is f triple prime at a over 6. And so when we substitute these numbers back in for these coefficients, we get that P3 of x is f triple prime of a over 6 times x minus a cubed plus f double prime at a over 2 times x minus a squared plus f prime at a times x minus a plus f of a. Notice this is just q of x. And what we did is we added one more term. It's a third degree term. The derivative went up, but it's still following the same theme of what we've done in our previous examples. So an extremely important pattern emerges from doing this, and we can do 1 more, 2 more, however many you need in order to see the pattern. But what happens is when we do an nth degree polynomial approximation, and I'll call it a piece of capital N, it will be a function of x. We want it centered at x equals a. What you're going to get is the nth derivative of f at a over n factorial times x minus a to the n, plus we're going to count down on the derivatives. So this is an f n minus first derivative evaluated at a over n minus 1. So as this counts down, this matches. N minus 1 factorial times x minus a to the n minus 1. We'll keep counting down on the derivatives until we get all the way to a first derivative, and so the denominators will be all the way to that 1 factorial, and then we end with a constant term here. You can think of this as the 0th derivative term. 0th derivative just means original function. This, we claim, is the best nth degree polynomial approximation for f at x equals a, in the sense that this creature is going to match f, f prime, f double prime, all the way up through the nth derivative of f at x equals a. And the way these coefficients were found, notice that there's n plus 1 of them, the way that they were found was by imposing those n plus 1 conditions, those matching conditions, and solving the resulting equations. This creature is called the nth degree Taylor polynomial because a mathematician named Taylor did this not long after Newton first started writing his calculus. And so these got named after him. And I know I called this P sub n of x, but our textbook and almost all the calculus books call these T sub n of x in honor of Taylor. So this is called the nth degree Taylor polynomial for f at x equals a. And so this is exactly the same formula that we had up here. And if you wanted to write this a little more compactly in summation notation, we have this form. So one other little note here is that if the center happens to be 0, if it's centered at 0, these are also called Maclaurin polynomials in honor of the mathematician Maclaurin. So Maclaurin polynomial is just a special Taylor polynomial. It's not wrong to call it a Taylor polynomial, but if you see this in your homework, I wanted you to know that this just means a Taylor polynomial with an a of 0. So notice that if I could put this on the screen at the same time, notice that if you were to compute this when capital N is 1, so you're doing the first degree Taylor polynomial, if you were to string this formula out, you would just get, with the first degree Taylor polynomial, you would get our linear approximation from calculus 1. So the equation of the tangent line, or the linear approximation that you found in calculus 1, is the first degree Taylor polynomial for f at x equals a. And the q of x that we found above, that best quadratic approximation, is t2. And the cubic approximation was t3. And we could do this for any degree polynomial that you want. This is the way the best approximation always comes out. So what's the key point about Taylor polynomials? The idea is that Taylor polynomials enable us to approximate complicated functions using very simple or simpler functions that are polynomials. Let's look at an example. So let's take the function f of x equals the square root of x. Let's find the first degree Taylor polynomial, the second degree Taylor polynomial, the third degree Taylor polynomial, and we want them centered at x equals 1. And after we found those polynomials, let's use each one to approximate the numerical value, square root of 1.3, and let's compare how they do. Okay, so let's organize our workflow. When we look back up here at the formula for the Taylor polynomials, we see that if you're going to find t1, you need to know up through the first derivative of your function evaluated at your a. So when you go to find t2, you need to know up through the second derivative. When you go to find t3, you need up through the third derivative. So I'm going to go ahead and organize my work. I know that I'm eventually going to find up through t3, so I'll go ahead and get the function value. My a here is 1. My a here is 1. It's where I'm building the approximation. So if f of x is x to the 1/2, then if I evaluate this at my a, so f of a is 1. If I calculate the first derivative and then evaluate that at my a, I get f prime at 1, which is just a half. F double prime at 1 is minus 1/4. F triple prime at 1 is 3/8. So I've got all these pieces together, and now let's just follow the formula. T1 of x from above in green is f prime at a times, parentheses are very important, x minus a plus f of a. Well, my a was 1, and now f prime of 1, I've recomputed up here, it's 1/2. I leave this alone, and f of 1 I computed was 1. Now you could simplify this, it doesn't matter. This is a perfectly good form for me, and it should be for Achieve to leave your answer in. When we go to find t2, we just follow the formula, which is for t2, it's f double prime at a over 2 or 2 factorial times x minus a squared plus f prime at a times x minus a plus f of a. My a is 1, so I'll put the 1 in. Everywhere I see an a, I'll put a 1. I already computed f double prime at 1 was negative 1/4. F prime at 1 was 1/2. F at 1 was 1. And now I'll just simplify that just a little bit, but I'm not going to multiply this out. Let's just leave this. This is a perfectly good form to leave it in. And notice this is a second degree polynomial. This was a first degree polynomial. Let's do it for one more. For t3, we have f triple prime at 1 over 3 factorial times x minus 1 cubed plus f double prime at 1 over 2 factorial times x minus 1 quantity squared plus f prime at 1 times x minus 1 plus f at 1. So if we've already calculated f triple prime at 1, f double prime at 1, f prime at 1 above, and if we just take this and divide by 3 factorial, remember that's 3 times 2 times 1, and that comes out to be 1/16. When we do f double prime at 1 over 2 factorial, we get minus 1/8. We do f prime at 1, we get 1/2, and f of 1 was 1. So here is the third degree Taylor polynomial, T3 of x, for this function. And now let's finish off what they were asked for in the example, and let's look at the approximations that these polynomials give us at 1.3. So here when we take T1 and evaluate it at 1.3, well, that just means we take our first degree Taylor polynomial here, T1. We just take that first degree Taylor polynomial, we evaluate this at x equals 1.3, and we see what we get. This comes out to be 1.15. If we take our T2 polynomial, we evaluate this at x equals 1.3. This comes out to be 1.13875. And then if we take our third degree Taylor polynomial approximation, we evaluate that at x equals 1.3. We get 1.14044. Now if we compare each of these with the exact value, square root of 1.3 is 1.14018. We see that as the degree of the Taylor polynomial increases, notice our approximation is getting better and better in the sense that it's getting closer and closer to the true value. And that's no surprise. As we work harder to get a higher degree polynomial approximation, the benefit of doing so is that we get a closer and closer approximation. So we've done that algebraically or numerically. Here let's look at it graphically. So in blue, this is the curve y equals the square root of x each time. And then here is T1 of x. It's just the linear approximation at 1. So here the red is just the equation of the tangent line. It's T1 of x. We can see that that's a good approximation when you're close to 1. As you get farther and farther away from 1, notice the red curve and the blue curve diverge. So it is not as good of an approximation, but remember, this is an approximation centered at 1, so it's going to be good in a neighborhood of 1. Here in the orange, we see this is the T2 approximation. It's quadratic. There's not a lot of the graph shown here, but this is a parabola. Notice that it is centered at x equals 1. Notice that it is a good approximation. In fact, it's a better approximation, meaning that the orange matches the blue curve longer, or for a longer x interval, than the red line matched the blue curve. And then in green, we have the third degree Taylor polynomial approximation centered at 1. And notice that it's an improvement. It matches the blue curve longer than the orange parabola did. And just to kind of show that, I put all three on the same coordinate plane and we zoomed in. I know that the picture is quite busy, but keep in mind the blue curve is y equals the square root of x, or f of x equals the square root of x. The red is the T1, the orange is the T2 of x, the green is the T3 of x. And so you notice that as we increase the degree of the polynomial approximation, the accuracy is improving both graphically, and we saw that the same thing happen numerically. The key ideas here are that if you find an nth degree Taylor polynomial approximation, that t sub n of x will be an approximation for f as long as x is close to a. We'll make this more precise in just a few minutes. If you want to make your approximation better, your approximation will always improve as your x value gets closer and closer to a, or another way to make your approximation improve is to let your n increase, the degree of your Taylor polynomial approximation. So can we quantify the error in such an approximation? In other words, if we use T3 at 1.3 to approximate the true value of the square root of 1.3, how much could we be off by? Well, Theorem 2 comes to the rescue and quantifies that error. It gives us an error bound. So note in this theorem here they use little n to denote the degree of their Taylor polynomial. I use a capital N, but the idea remains exactly the same. So the error bound theorem says, assume that the n plus first derivative of f exists and is continuous. Let k be a number such that the absolute value of the n plus first derivative of f at u is less than or equal to k for all u between a, the place where you built your approximation, and x, the value at which you're applying your approximation. Then the absolute value of f of x minus t sub n of x Notice this is just the absolute error of the approximation because we're taking the absolute value of the difference between the true value of f at x and the approximated value by t sub n of x. So the absolute error is bounded above by this constant k times the absolute value of x minus a to the n plus first power over n plus 1 factorial. So see the text for the proof. Let's jump into an example and see. And one of the most complicated things for students usually is to understand the role of this k. And this k is just a bound on the n plus, for the absolute value of the n plus first derivative on the interval between the place where you built your approximation and the place where you're going to use your approximation. So let's see how that plays out in a practical example about how you select this k. All right, so let's give a bound on the errors in example 1 when approximating the square root of 1.3 with t1 at 1.3. In other words, we build the first degree Taylor polynomial approximation. We evaluate it at 1.3 in an effort to approximate this. Let's see how much error is involved in that. And then let's also do the same thing when we use the third degree Taylor polynomial. We evaluate it at 1.3, and we want to know how far we could be off from the true value here. Well, in the first of these, here our capital N is 1, so let's look at our error bound theorem, and let's just make sure that we understand the pieces here. So our function here is f of x is the square root of x. So the x where we're performing our approximation is at x equals 1.3, so we have absolute value, square root of 1.3 minus t sub, in this case, we're doing t sub 1 at 1.3, our n is 1. So that means we're going to get less than or equal to the k. I'll show you how we get our k in just a second. K times absolute value of 1.3 minus 1, our a is 1, our x is 1.3. We're raising it in this case to the second power because our n is 1, divided by 2 factorial. Remember, these should always match, and they should be 1 higher than the degree of your polynomial. And so how do we find this k? Well, remember, the k is a bound on the absolute value of the n plus first derivative of f on the interval between the place where you built your approximation and the place where you're using your approximation. So if you think about, we're doing a first degree Taylor polynomial. Our n is 1, so we need to get our hands on the second derivative. If you look above, this is the second derivative of that function. We're going to take its absolute values. Now notice this is positive, so the absolute value really only affects this part and gets a 1/4. But now think about an upper bound for this. This function, we got fortunate here. This function is a decreasing function, and so it's going to max on the interval from 1 to 1.3. It's decreasing, so it's going to achieve its maximum value at the left end point of that interval. It's going to achieve the maximum value when x is 1, and so when x is 1, this just comes out to be a 1, and we get off pretty light because this is just a 1, this is a 1/4, and we get that our k is 1/4. So the k, in practical terms, it's the maximum of the absolute value of your n plus first derivative on the interval from a to x. In this case, it was 1. So our k, this maximum was 1, which made our k 1/4. So our k is 1/4. We can compute all of this rather easily, and it comes out to be 0.01125. So what that means is when we use this approximation, the most that we could be off by is 0.01125. So that's a pretty good approximation. Let's try the same thing with n equals 3. So if we do this with n equals 3, we still have our absolute value of our f of 1.3 minus our t sub n at 1.3. So our n is 3. So we're going to have to get our k. We'll get that in just a second. We're going to do absolute value of x minus my a to the n plus first power over n plus 1 factorial. My n is 3, so these are 4s. Now this is easy and this is easy. 4 factorials, just 4 times 3 times 2 times 1. The real work here is how do I get the k? Well, to get the k, I need to get my hands on the fourth derivative of my function. So if you scroll up, we found the third derivative of our function. If we find one more derivative, we'll get this. We take absolute values. Again, the absolute value, everything here is positive, so the absolute values don't matter. Again, we're fortunate that this is a decreasing function on the interval from 1 to 1.3. So that means its maximum is going to occur at the left end point. It's going to occur at 1. And this evaluated at 1 is just 1. So our k is 15/16. We'll put this in for our k. We'll do the arithmetic here. And when it's all said and done, we get a value of 0.000316 for the bound on our absolute error. So notice our n increased from 1 to 3, and notice how much our absolute error shrank. So the approximation definitely improved by cranking up the n here, even though we kept the value that we were approximating at exactly the same. Okay, as one more prototype example, and let's play the game backwards. Instead of us being given an n and calculating the error, what if we said, hey, I need an error that is no bigger than a certain number, and I want you to find the smallest Taylor polynomial that makes that happen. This is very practical. Sometimes you know the degree of the approximation and you're wanting to quantify the error. Sometimes you just, in the practical application, you have a tolerance for the error that you can withstand, and then you want to calculate the smallest Taylor polynomial that'll make that happen. So let's find the smallest n such that t sub capital N of x, centered at x equals 0, will approximate the function f of x equals sine x at x equals 0.5 with an absolute error of no more than 10 to the minus 3. So now, instead of giving the n and finding the error, we're being given the error and asked to find the smallest n. Well, let's just go back to our error bound theorem. Error bound theorem just says the absolute error between the true function value sine at 0.5 minus the nth degree Taylor polynomial approximation at 0.5. And remember, this is a polynomial approximation built at x equals 0 here, but then we're using it to approximate at 0.5. That absolute error, we want it to be less than 10 to the minus 3. So we want this to be less than or equal to 10 to the minus 3. Find the smallest n that makes that happen. Well, let's just start with this. This is our absolute error. So from our error bound theorem, we know that our absolute error is bounded above by some k times our x minus our a raised to the absolute value raised to the n plus first power over n plus 1 factorial. In this case, this number is easy to compute. This number we don't know yet because we haven't picked our n. And now what about our k? Well, in general, k needs to be a bound on the absolute value of the n plus first derivative of our function, and we don't even know what our n is going to be. But thankfully, we have the function sine x, and so if you just look at its pattern of derivatives, it doesn't matter what order derivative you take. What I can say with confidence is that no matter what order derivative you take, all of these functions have their absolute values bounded above by 1, because they all bounce between minus 1 and 1. So their absolute values are all bounded above by 1. So we got off pretty light here again because of the nature of our functions. So we take our k to be 1, and this will be a true bound no matter what our n is. And so now we look at this quantity, and we don't know what our n is, so we just whip out our calculator and we say, well, let me calculate this. Let's see what it is when n is 1. And I went ahead and did this ahead of time. If we did this when n is 1, we got that this comes out to be 0.125. If n is 2, this comes out to be 0.0208333, and so on. And so we see that there's no way around this. We just have to one by one compute these. And we were given a tolerance that our absolute error needed to be less than 10 to the minus 3. And so we're looking for the first time this gets less than 10 to the minus 3. So it looks like it happens right here. It happens at n equals 4. Of course, once it gets smaller here, the error is only going to reduce when we pick a larger and larger n. So these are going to monotonically decrease. So the smallest n that makes this happen is n equals 4. So now as a practitioner, you could go back and say, if my application demanded an error, an absolute error of no more than 10 to the minus 3, then with confidence, I can take a 4th degree Taylor polynomial approximation, use that in place of my function, and I'm guaranteed that I will meet the error requirement. Now, the last thing that's in this section is we've talked about approximations and quantifying error, but if you go back to how we calculated Taylor polynomials or Maclaurin polynomials using the formulas that were in red and green back earlier in the notes, there are some famous Taylor polynomials that you just need to commit to memory. And these are all Maclaurin polynomials except for ln of x, because since that's not defined at 0, we do its Taylor polynomial centered at 1. But if you just go back and apply those formulas to the function, say, e to the x, you get that this is its nth degree Taylor polynomial. So for example, these first three terms, this is the second degree Taylor polynomial or Maclaurin polynomial for e to the x, for the function f of x equals e to the x, centered at x equals 0. This would be the third degree Taylor polynomial, and so on. If you did sine x, here are the terms in the Maclaurin polynomial for sine x. Here are the terms in the cosine for the cosine function of the Maclaurin polynomial, and same for the natural log of x. Now this is a Taylor polynomial, it's at 1. And here our familiar friend, the geometric series. We've seen this kind of pattern before. Notice this is still finite because we're only doing Taylor polynomials, so it terminates after a finite n. But these are definitely ones that you should commit to memory. And here they're writing them out in their expanded form, but notice you could also write them in their sigma form, and you should be comfortable working with both.